Okay, something called oxidation numbers. So this is still chapter 7. Okay, and so oxidation numbers are kind of a theoretical value for us. And they're a little bit hard to kind of really nail down what oxidation numbers mean. And so I want you to get out your textbook because I want to read a little bit about kind of the definition of an oxidation number and what they're about. I think they're on page 232. Okay, on page 232, I want you to read just that first paragraph about oxidation numbers, and it'll give you a little bit of an introduction as to what they are, what do they mean, all that kind of stuff. Okay, so 232. Okay, oxidation numbers are difficult to pinpoint exactly what we think they are, right? It's similar to a charge, similar to a regular charge, but it's not quite all the way there, right? So in an ionic compound, we have a metal and a nonmetal. And each of those have very distinctive charges. And what those charges tell us is within that compound, the electrons are located here, right? That would give us a negative charge, or the electrons are missing from this side, which would give us a positive charge. Does that kind of make sense? In an ionic compound, right? So in a covalent compound, which your book calls molecular compounds, we assign what we call oxidation numbers to help us determine where our electrons are located within that molecule. Okay, and so it has to do with their structure, with the way atoms are bonded to each other, but essentially the oxidation number kind of gives us like this mini charge value. It kind of tells us if we would have a positive number assigned to an element, that means that the electrons are not near that element, right? A positive charge or a positive oxidation number would tell us that they're missing electrons. Whereas if an element had a negative oxidation number, that means that more electrons would be surrounding that element. Does that kind of make sense or not so much? Yes or no? Okay. All right. Let's just take a look at a structure real quick. We haven't gotten to drawing molecules yet, which is what we'll cover next chapter. But let's look at a really simple example of a covalent compound. Okay. If I have a compound between hydrogen and fluorine, okay, can anyone tell me what that might be named? HF? Yeah, good. Hydrofluoric acid? Good. Okay. If I have a structure that looks like this, why don't you tell me how many electrons does fluorine have in its outer shell? Do you remember what the term valence electrons means? Right? How many valence electrons does fluorine have? It has 7. And how many valence electrons does hydrogen have? 1. It has 1. So together, in this compound that I'm showing you here, it has 8 electrons. And so fluorine, if I draw my electrons in the form of dots, has 7 electrons. Okay? And hydrogen has 1 electron. I'll draw hydrogens different. Okay? This is kind of an introduction to our next chapter, but hydrogen has 1 electron. Okay? So together they have 8. So those two right here form what we call a bond, right? And we're kind of getting ahead of where we need to be right now. But when we talk about oxidation numbers, you see how all these electrons are located really near fluorine, right? Fluorine might be given a negative oxidation number because all of the electrons are crowded around fluorine, right? And a charge or an oxidation number means that it's telling us where the electrons are located in general, okay? That's really the overview of the theory that you need to know, but now I'm going to tell you how we mathematically can solve for oxidation numbers, okay? It's much... It has more definite rules than the overall definition of it, okay? So when we solve oxidation numbers, there's a whole list of things, and you can see them in your book here on page 232, but I'm going to give you a shortened version of how we can assign an oxidation number, okay? So the first thing we need to look at when we assign an oxidation number, and you can think of that as kind of a mini charge, right? The first thing we think about when we assign an oxidation number is that an elemental atom, and I'll tell you what that means here in a second. An elemental atom always, oops, I can't spell. All right, so elemental atoms always have an oxidation number of 0. Okay, and I'll explain why kind of this is. Elemental atoms means that if we're just looking at an atom that's by itself, so if we just look at sodium, or if we look at oxygen gas, or if we look at hydrogen gas, or whatever it is, it's an element that's just bonded to itself that has an oxidation number of 0. And the reason that is because if we're looking at the distribution of electrons within this molecule, let's say an oxygen molecule, wouldn't each oxygen want those electrons with the same amount of force or whatever you want to think about it as, right? Each of those oxygens, does one of them want electrons more than the other? No, they behave the same, right? Each of those oxygen atoms behaves the same. So one of them is not pulling electrons toward itself more than the other. So there's no uneven distribution of electrons. So when we talk about the oxidation number for single atoms or elemental atoms, it's just 0. There's no charges because everything's even, right? Okay, number 2, there's a few of these elements that, or I call them the big 3 elements, they get priority over others, okay? And so the first one is fluorine. Okay, so fluorine always has an oxidation number of -1. Okay, fluorine always has an oxidation number of -1. And if you think about it, that reflects its charge as well, right? Its formal charge. Okay, so I'm going to briefly describe here why fluorine gets the most precedent here, okay? Have you heard about something called electronegativity? Right, you guys talked about periodic trends a little bit at the end of last semester. We talked about electronegativity. Maybe? Not so much, okay. Electronegativity has to deal with how badly an element wants to take electrons from something else. Okay, does that make sense? Electronegativity means how badly an element wants to take electrons from something else. And fluorine is the single most electronegative atom that we have. So on the periodic table, fluorine is the single most electronegative atom. It will take electrons from anything and everything all the time. So anytime it's bonded with something, it's always going to be pulling those electrons toward itself, which means it gets to keep its charge as its oxidation number. It's always going to have an extra electron surrounding it. Okay, so that's the rule for fluorine. It's the most electronegative. It wants electrons more than anything else. So it's always going to have an oxidation number of -1. Okay, and if all this talk about charges and everything is still a little bit over your head, that's okay. Try to just get the rules kind of in your head for now, and it will make sense as we start putting things together. Okay? Rule number 3 is the second of our big 3 elements, and it has to deal with oxygen. Boys, stop talking, please. Oxygen has, I can write it out so you don't think it's something else. Oxygen has an oxidation number of -2. The only exception to this is when it's bonded with fluorine. Okay, and then its oxidation number can change. So oxidation numbers are unlike charges in that they have the ability to fluctuate. So it depends on what they're bonded with. Oxygen might not always have a -2 if it's bonded with fluorine. Okay, so their charge and their oxidation numbers are not always the same thing, but about 90% of the time they are. Okay? So oxygen has an oxidation number of -2, except when bonded with fluorine. The last of our big 3 elements is hydrogen. Okay, hydrogen has an oxidation number of +1. Okay, and the only exception here is unless it's bonded with a metal, in which case it is -1. Okay, most of the time I'm going to give you hydrogens with a +1 oxidation number so we can see. that it follows the rule, okay? But when we are looking at assigning oxidation numbers within a compound, right, a question with an oxidation number might be like this, H3PO4, right? I might give you this formula, and I would say assign the oxidation number for each element within that compound, right? Those are the types of questions that you'll be getting with oxidation numbers. So we're following these rules in terms of we go in the order, right? So I'm giving you the set of rules, and they go in that order. So if there's not fluorine, then we follow the rule for oxygen, and then we follow the rule for hydrogen, okay? So those rules go in a precedence order, okay? So those are our big three elements: oxygen, fluorine, and hydrogen. Okay. Rule number 5. The oxidation numbers must add up to the overall charge of the molecule. Yeah, Hannah.
What's oxygen's number when it's bonded to fluorine?
It would depend on how many fluorines it's bonded to. So it would depend. Okay, and I'll show you how we figure out that math in just a second when we start doing some examples. Yeah, good question. Could be that it turns to a positive. It could be that it's even a bigger negative, but most of the time it would flip to a positive because fluorine would be taking those electrons. Good question. Okay. Oxidation numbers have to add up to the overall charge of a molecule. So if I had this as a question, SO4 minus 2, and I wanted you to find the oxidation numbers, my totals of my oxidation numbers would have to add up to -2 because it's the charge of the overall molecule. Okay? If we wanted to look at this one again, H3PO4, what's the overall charge of that molecule? What's the overall charge of an ionic molecule? Okay, this is an acid, right? And acids have to be balanced. So the overall charge on this molecule is 0, right? Which means that in this case, our oxidation numbers would have to add up to 0. Okay, I know this seems really foreign right now. I promise when we start doing examples, it will start coming together. Okay, but I'm just trying to point out a few things as we go. So I know this might feel a little bit over your head still. That's okay. We will get there. Okay. Okay, last rule here. Okay, if none of the three, so if fluorine, oxygen, or hydrogen are not present, so that if they're not present in the molecule, then the most electronegative atom gets to keep its charge. As its oxidation number. Okay, now on page 161, it gives us this periodic table on the bottom that's called the Pauling scale. Okay, and the Pauling scale gives us each of these elements with its electronegativity value assigned to it. Okay, so we talked about electronegativity as how badly an element wants to take electrons from something else. So the larger the electronegativity value, the more it's going to take electrons. So if you look on here, fluorine has the highest electronegativity value. Do we see that? As you get further away from fluorine, our electronegativity values decrease. So the smallest electronegativity value is francium, right? Complete opposite ends of the periodic table. That means it has one electron in its outer shell that's far away from the nucleus. It'll give that electron away to anything and everything, right? It wants to get rid of it. Does that kind of make sense in terms of why it would want an electron, or do you want to go through that a little bit more? Okay, let's talk about why fluorine is the most electronegative. Why does fluorine want electrons more than anything else? Okay? Fluorine has how many valence electrons? How many valence electrons? No. Fluorine has 7, okay? And it's in the second energy level. So its outer shell, which is really close to the nucleus, because it's only the second energy level, has 7 electrons. The closer we are to the nucleus, the more impact that they have, right? So if I have 7 electrons, how many do I need to be happy? Right, I either need to get 1, to gain 1, or I need to give away 7. So which is easier to do? Get 1, okay? So fluorine has electrons that are really close, and it only needs 1. That's why it's the most electronegative. It will work really hard to take electrons from anything and everything. Okay, so now let's go to the opposite end of the scale. If we talk about francium's electronegativity, how many valence electrons does francium have? 1. And it's in energy level 7. So it's 7 shells away from the nucleus, right? And it's only got 1 valence electron. So to be happy, francium either needs to find 7 more electrons or give away 1. So which is easier? Give away 1. Okay, so it doesn't want to take electrons from anyone. It wants to give them away, right? So that's why its electronegativity is so low. Does that kind of make sense? That was a little excerpt to electronegativity. Okay, that might be new to some of you, but we need to be using this scale for our 6th rule for oxidation numbers. So if none of our 3 are present, the one on here with the largest electronegativity value would get to keep its charge as its oxidation number, okay? All right, do you feel completely overwhelmed right now? Yes, okay, that's all right. Okay, so we want to find the oxidation number for each element within that compound. Okay, so we want the oxidation number for each. And I'm going to show you kind of the method and the technique that I use to find that. If something else works better for you, you're welcome to write it a different way or whatever. But I'll kind of show you how I do this, okay? So what I know is in this molecule is one of our big 3 elements present. Yes, fluorine, right? And we say fluorine's oxidation number is always what? -1. So what I do is I like to put its oxidation number up top since it's similar to a charge, right? It's not exactly a charge, but it's similar. Okay, then how many of those fluorine atoms do we have in this molecule? 6, right? So I need to multiply its oxidation number times how many of them there are, right? So that gives me a -6. So I'm just going to write that down here at the bottom. That tells me its totals, okay? So up at the top are going to be our oxidation numbers, and at the bottom are going to be our totals, okay? When we give final answers, we want to give our oxidation numbers as final answers, not our totals, okay? Sometimes they'll be the same, sometimes they'll be different. Are we on the same page so far or not quite? Okay, we're getting there, okay. So I want this oxidation number totals, my totals, to add up to the charge of our molecule. And what's the charge of this molecule? 6. What's the charge? Was there any charge labeled on our molecule? No. Right, it was 0, okay? So this is the charge of the molecule. So we have to work backwards here with our math. What x -6 would get us to 0? What would x have to be?
6.
Right, it'd have to be +6, right? Those are our totals. But how many of those U atoms, which U is what, uranium or something? Okay. How many of those U atoms have to share that +6 total? Right? What's our subscript that would go right here? A 1, right? Only that +6 has to just be shared between 1. So that means our total is, our oxidation number is +6. Okay, you see how we kind of made a little box here? You still feeling totally lost? A little bit. Okay, that's okay. Uranium then would have a final answer of +6. Fluorine would then have a final answer of -1, right? These are our oxidation numbers. That's our final. The totals just help us get there, okay? So how we went from here to here is that we knew that there had to be a +6 charge, right, that had to get us to a 0, right? But there was only one uranium atom that had to split, right, or take, what's the word I want to use? Account for all of that +6 charge. If this would have been a U2 F6, we would have made this a +3, right? Because there would have been 2 atoms to split that +6 between. Okay, but since there was only one of them, that uranium atom is a total +6. Okay, yeah, sure. All right. Let's try H2SO4. Okay. Anybody name that molecule for me? H2SO4. Not hydrosulfuric, just sulfuric, right? Hydro would mean it would look like this, H2S, right? But it comes from sulfate, so it's got to be just sulfuric acid, okay? Not the topic for today, but good to practice. Okay, so here's what happens. Are any of our big three elements present? Yes, two of them are. So we go in order, right? No fluorine, but we have oxygen, so we go with oxygen. And we know oxygen's oxidation number has to be what? -2, so we put that up top, right? And how many of them are there? 4, so you multiply those down, which gives me a total of -8. Okay? Right, here's our totals down at the bottom. And here's our oxidation numbers up top. Okay? Is there any charge on this molecule? No, there's not, right? H2SO4, no charges. An acid has to be balanced. This has no charges, right? Do we on the same page with that or not quite? Yeah. Okay, no charge. So that means my totals have to add up to what? 0. Have to add up to 0. Okay, so when we have a molecule that has 3 elements, we work in order of our rules, okay? So we went oxygen, now we skip over and go to hydrogen, okay? And it's best, even if you think about it, you work your outside in. So this element that's in the middle is usually the last one that gets adjusted. Okay, that's something to think about. So let's skip over to hydrogen. What do we know about hydrogen's oxidation number? It's a +1. Okay, so we know it's +1, so we're automatically going to put it up on the top. Right? Does that part make sense or not quite? We're going to multiply that, right? There's 2 hydrogens that each of those have a +1, which gives me a +2. Okay? So we have 2 plus x minus 8 has to equal 0. So what does this x value have to equal? A +6 or a -6? +6, okay? So +6 has to go here. Now, how many sulfur atoms have to split that +6?
1.
Just 1, right? So that means sulfur's oxidation number has to be +6.
Oh, so you just bring it up?
Yeah, we just bring it up because this is a 1 here, right? So we just would multiply it back up, but we don't have to, or divide it really, but okay, so if we give our final answers here, hydrogen has an oxidation number of +1, sulfur has an oxidation number of +6, and oxygen has an oxidation number of -2. Right? We need to understand the fact that these don't not have to add up to 0, right? Our totals are what have to add up to 0. Okay? So that part does not need to add up to 0. Okay, what other questions do we have? Is it getting a little bit clearer? Kinda? Okay, let's do a couple more. Let's try... I want to do N2O5. Okay, so what do we know about oxygen? So -2 here. Our total pulls down. We multiply those together. So we have a -10. Does this molecule have any charge on it? No. So we want these to add up to 0. Okay, what value has to go here to make that add up to 0? +10. And how many nitrogen atoms have to split that +10? 2, right? So you could divide by 2 to get it back up here. So +5. Okay, so that means when we give our final answer, nitrogen is equal to +5, and oxygen is equal to -2. Okay. Questions here? So you kind of should start and do a little box, right? You work your way around to finish. If you've got 3 of them, you should really work from outside in. Okay? Usually the elements that will not represent their true charge are things like phosphorus, nitrogen, sulfur. See where those are at on the periodic table, kind of right around oxygen? Those guys right there, carbon, they will be really fluctuating with their oxidation number, right? Hydrogen is always really set. Oxygen is always really set. But those in the middle, that you'll see in the middle of polyatomic ions, things like that, those are the ones that will really fluctuate, so they need to go last. Okay? All right, let's try a couple more here. Yeah, what's the name? I heard somebody say it, I think. What's the name? Hydrochloric acid. Good. Okay, we have hydrogen, so this time we're going to start on the other side. Hydrogen's a +1. We know it needs to add up to 0, which means chlorine has to be a -1 total, and we only have one chlorine atom. So this was pretty simple, right? These both get to keep their regular charges. Okay. Let's try one without one of the big three. Okay, GeCl2, germanium chloride. So when we don't have one of the big three, what's the rule that goes with that? Not quite, not quite. Which one gets to keep its charge as its oxidation number? The most electronegative. So that means the one closest to fluorine gets to keep its charge. So which of those is closest to fluorine? Chlorine. So what's chlorine's regular charge? -1. Okay, so it gets to keep its charge as its oxidation number. And so there's two of them, right? Which gives us a -2. What do we want this to add up to, our totals? We need them to add up to 0, and that means germanium has to be a +2. So our final answers are -1 and +2. Okay. Now let's try some with a charge. With the charge. What if I gave you... Does anybody name that one? It's a polyatomic ion?
Chlorate.
Chlorate, very good. Chlorate. Okay, so I'm going to put these in a different color so we don't get them mixed up. Oxygen is a -2. We want them to add up to -1, so this value here has to be +5. There's only one chlorine atom. Oops. So we should get a +5.
So wait, if we got, like, what if there was 2 chlorine?
Yeah, that's a great question. Never happened.
Really?
Yeah. Okay, so he's asking if this was Cl2O3, right? It wouldn't work because we can't have a half of an oxidation number, right? We couldn't have 2.5 up here. So if that's happening, something's wrong. Okay? Very good question. Okay, our final answers here would have been oxygen or -2, chlorine is +5. Okay. Like this, if I had lithium phosphate, Li3PO4 is lithium phosphate. Right? I said there's a couple of ways we can do this. We can work outside in, or the way you can think about it is we can solve the polyatomic ion by itself and then add lithium onto it. Okay, so I'll show you what that method looks like. Okay, so if I wanted to solve this and I had to break it into its polyatomic ions, I would separate it out, right? Lithium +1 and phosphate, which is PO4 -3. Right? I'm going to separate them to help me solve. Because it does not matter if they're together or separate. The oxidation numbers should be the same. Okay? So in phosphate itself, oxygen is a -2, right, which would be a -8. And I want my totals to add up to -3, which would have to make phosphorus what? +5. Okay? So the only thing that's left for us to look at over here is lithium. And its oxidation number is already given to us, right? Its oxidation number is the same as its charge. So our final answer here would be lithium +1, phosphorus +5, or oxygen -2. Right? It works the same way if we work outside in. But if we have a metal here, they usually get to keep their charge. Okay? This is the one that does the most fluctuating. Whatever element's in the middle there is the one that will most of the time make a change. Okay, I'll fix that here in a second.